today I want to begin by finishing the proof of the zone theorem, and then we will discuss some of the applications of the zone theorem and arrangements. Let me just go over the notation once again. So, L is a set of n lines, and I will use A L to denote the arrangement, which is a planar subdivision induced by the set of lines. For each face f, two dimensional face f, I will use an n f to denote the number of edges. It does not matter whether I choose edges or vertices, because they are roughly the same. If the face is bounded, two quantities are the same. If it is unbounded, it will be differ by 1. Okay. Now, if I take another line, zone is a set of faces of the arrangement that intersect L. So, just to remind you, zone L is so this is the set of okay. So, in this picture those dashed faces are the faces in the zone, and what I had defined was so that is a number of basically the number of edges in the faces that lie in the zone, and I denote the quantity mu n is the maximum this quantity over all lines, and the theorem that I wrote was that mu n is order of n. So, this is what I want to prove today, and once I have done this, that will imply that the algorithm I had described for constructing the arrangement takes n square time, because inserting each line takes linear time, and then the whole thing will take n square time. Okay. So, suppose this is a arrangement, the zone. What I will do is, first I will count the number of edges in the zone that lie. So, this is the line L, whose zone I want to count. First, what I will do is I will count the number of lines that lie above, edges in the zone that lie above the line, and by multiplying it by 2, I will also count the number of edges that lie below the line in the zone. Okay. I will do some double counting, because the edges that intersect the line, they will be being counted twice, and I will compensate for that, but it is not going to be important. So, first observation is, first thing you observe, question, how many faces does this line L intersect? How many faces are in the zone? Maximum n, am I right? Because or n plus 1, because each line intersects the red line only once, and if you so, you get n plus 1 intervals, and each interval corresponds to one of the faces that is in the zone. So, right. So, this is a face 1, 2, 3, and da da da. Okay. So, the number of faces in zone L is at most n plus 1. Okay. So, let us look at one of the faces and look at the portion that lies above it. So, let us I want to draw a complicated face which I will do. So, let us look at this face. There is a topmost vertex, okay. So, this topmost vertex, if you look at the portion of the face that lies above the line, the topmost vertex divides this boundary of this face into two parts. What I mean is the following. Here is your line L, whose zone you are looking at, and let us look at a complicated face. This is the topmost vertex. Okay. So, there is a left chain and the right chain, this divide. So, here is a one set of edges and here is another set of edges here. So, let us call this as a left chain and let us call this as a right chain. Okay. Now, the topmost edge in each chain, I will charge it to that face itself. Okay. So, let me write it down. Okay. And charge the top edge of left and right top edges of chains to that face. Okay. So, what you are doing is for each face you are charging two of its edges to that face, and I know there are only n plus 1 such faces. So, this is a total of, ignore 1 for now because I do not want to be picky. So, this is roughly 2 n edges, all right. So, what I have done is this I have charged, this I have charged. What I have to now count is these edges, this I have not accounted for. Okay. And here is a nice claim. So, let us assume that these edges I have marked because I have charged them. So, I marked them. So, this I have marked. So, these are unmarked edges. Okay. So, the claim is each line. Okay, so let me put this way. Let's focus on the left chain, and the right chain I will do the same way. Am I right? So, let us focus on the left chains. And what I will do is the following. Let me say it and then I will say the claim. So, you are looking at this edge and this edge, and let us label these edge lines L1, L2, L3, L4. Okay. So, just to let me sort of repeat myself again, what I did was I took each face on the zone, took the topmost vertex. The topmost vertex divides its boundary of the face into two chains, left chain and the right chain. The top boundary of the left chain and the top edge of the right chain, I charge to that face, to that vertex. Now, the rest of the let us look at the left chain. What I will do is each unmarked edge in the left chain on any face, I will charge it to the line itself. Okay. So, before I let me finish the charging scheme. Each unmarked edge on the left chain is charged to the line of L on which it lies, and do the same for the okay. Is the charging scheme clear? Before I give the crucial, before I give the punch line. So, this is not just for one particular face, this I do for all the faces that lie above the portion of the face that lie above the line. So, for each face, the two edges are charged to that face, so that gives you 2n, and the rest of the faces which have edges that I have not charged, that have not been charged, I charge each edge I charge to the line itself. Okay. And the claim is the following. Yeah.
What's the difference between these two? I mean, why did we treat the other?
You will see, because wait for the punch line. Here is a lemma. Each line of L is charged at most once by the unmarked edges on the left chains. Okay. So, this is the punch line, and the same is true for the right chains, and the similar claim is true for the right chains, and the same is true okay. Let us ponder a minute before we prove this lemma. If this is true, what this says is that each line is charged at most once by the left chain and at most once by the right chain. So, it means that I have the total charge I have made is only 2n. So, 2n are such edges, and 2n the edges that I charge to the faces, you get it 4n, and then this is only the portion above the line, then you repeat the same thing below the line, you get 8n. Okay. So, this is this finishes the proof of the zone theorem. Okay. So, now there is some double counting going on, and if you want to improve the constant, you can be more careful. The argument that I am giving you is sloppy, but this shows is that the total complex of the zone is at most 8n. So, let me repeat it, because what I did was first I focused the portion that is above the red line, and for each face on the zone I charge two edges on the top left and top right to the face, rest edges I charge to the line that to which they belong to, and then I claim that each line is being charged at most twice, once by the left and once by the right. So, that basically finish, and repeat the same argument for the below, it gives you total order of n. So, the main thing that is left now is to prove this lemma, that why each line is being charged only once, and that will also answer his question why I am doing it this way. And it is easier to do the proof by picture. Suppose this was, let us say, an edge or that was unmarked, because let us say this was somehow the face it looked like, and this was not the top edge because top edge something like is somewhere here. So, this is an unmarked edge. Okay. Well, if I want to complete it, actually I have drawn it slightly smaller. If you, in this case it is goes, let us say that there is another, somehow that is how it looked like. So, this is an edge that is does anyone see that why a line, this line L, if it is being charged by this edge E, it will never be charged by another edge. That is right. So, what happens is that once this line intersects, so suppose it is charged here, okay, then what happens after that is that since this was not the top edge, right, this is the top edge, it means that line L is being intersected by L prime, and after this L prime lies below it, L, am I right? After this intersection point, line L prime lies below L, and what is happening is that L prime is shielding L from appearing on the zone again, because there is no way that after this one that L can show up on the, this line can show up on the zone after that again, because it is being hidden by, always being hidden by this line. Because if it appears, if you notice that if it appears, an edge appears in the zone, you can connect it by straight line to this line without intersecting any other line. But now, if you take any other point here, when you try to connect it to the red line, you will always intersect the this line L prime. So, that, but this argument crucially uses the fact that this was not the top edge, because if it was at this edge, for this edge I could not make this argument, because there is no edge which is lying below it to the right of it here, and that is why I did this charging scheme in this way. So, this finishes the proof. So, if you want to write sort of say it more formally, then what you have to say is that after, since this is not the top edge, there is another edge L prime that lies that intersects, appears in the zone after it, and this intersection point after this face L always lies above L prime. As a result, L cannot show up on the zone to the right of this intersection point, it means to the right of this face. As a result, it is being charged only once, and the same thing happens to the right edge, right chain. Then you have to talk about the left part, and that completes the argument. So, this shows that the zone theorem is true. This proves that this implies that mu okay, and that finishes the algorithm. Is this clear, or any questions?
Sir, what about the part of edge to the left of the I mean the face? This face can't it appear on the
sorry, say it again.
The part of the edge to the left of this face, the face we are considering. Can you just get back the figure?
This figure?
Yeah, we walk left on the zone. If you walk left on the
So walk from the left. Ask the first time when this line appears on this zone, right? Ask the question when is the first time. So, I am talking about on the left chain, am I right? So, ask the question when does this line being charged on the left chain first time, and this is let us say this is the first time this has happened. It has never happened before that, and because after what I am arguing that once it has happened, it cannot happen again. Does this make sense, or any? Okay. Now, so far I talked about the arrangements of lines in 2D. One can talk about the similarly arrangement of hyperplanes, or let us say in 3 dimensions you have a set of planes. If you take a set of planes and draw in 3 dimensions, you will get another arrangement, but it will not be a planar subdivision, it will be a spatial subdivision. And you can still talk about the notion of the zone, that you take another plane and ask about the complexity of the faces that intersect this new plane, and you can incrementally again construct the algorithm. And so, you can talk about, let us say H is d dimensions, and you can talk about the arrangement of H, and then we can also talk about the zone of set of and again you can talk about the maybe complexity as number of vertices or some convenient way of talking about it. And now, since you are talking about d dimensions, let me use two parameters n and d to denote in what dimension we are. Okay. And the theorem is, which I will not prove, it is now I should say that the complexity of the arrangement is order of n to power d, because every d tuple is the way in 2 dimensions every pair of lines intersect at a single point. In 3 dimensions, if you take 3 planes, intersection of 3 planes is a single point. So, the complexity of the arrangement in 3D is n cube, and if you are in d dimensions, if you take hyperplanes in d dimensions, every d of them will intersect at a single point. So, number of vertices in d dimensions will be n to power d. So, the complexity of the arrangement in d dimensions is n to power d, and what is known is that the complexity of the zone in d dimensions is only n to power d minus 1. So, this incremental algorithm can be extended to higher dimensions. You add a hyperplane one after another and construct the arrangement, but the proof is much more complex, and it is a recursive argument, and I will not go through it. If you are interested, I can give you the reference. Now, let me do the proof of the last time what I did again, and then I move on. So, last time I had proved n square. That is what I had proved last time, and the proof was as follows. First, some simple algebra, right. So, if you want to write x square, something you can write it as 2 times x choose 2 plus x. The second term is, we know that it sums to n square, because that is the total complexity of the arrangement, number of edges or vertices in each face. So, the only thing that is left is to bound this quantity, and the claim is so, what it sort of says is that the 2 times n f choose 2 is nothing but do the following. You have a set of lines, remove one of the lines, repeat the following experiment for each line, pull out one of the lines, look at the arrangement of the remaining lines, and think of the zone of this line in this arrangement. Okay. And look at the complexity, and you sum it, do it for each line one after another, and that sum is the same as this one. And why is that? So, let us say, just to keep the life simple, maybe let me just keep just 4 lines, just so that you can sort of follow what is going on. So, NF twice NF choose 2 is for every face. So, let us say fix one of the faces. I am counting the number of pairs of edges, right, that is NF choose 2 means, and twice is mean that I count each pair twice. Okay. So, I do care about the pairing ordering. Okay. Now, in order to do that, suppose look at all pairs, fix a line L, one of the lines, and look at all the pairs that I am counting that involve this line. Okay. So, for here let us call this line L. So, for this edge I will count with this one, this one, this one and this one on this side, and this one and this one on the other side, am I right, because those are the pairs this edge will involve, and similarly for here this it will correspond to some other pairs and so on. But let us focus on this one, on this line, on this face. If I pull this line out and look at its a zone, so think about that, I pull this red line out and I am looking in the zone of this red line in the arrangement of remaining things. And when I am counting the complexity of the zone, what am I counting? For each face that it intersects, I am counting how many edges are there. And so, for this line, for this edge in this face that is intersecting, I am counting this one with this one, this one, this one, this one, this one, this one. That is how I did the counting. So, what I did was, and I do it for each such face. So, what I did was I counted all the pairs that involve this line when I counted the zone here. So, all the pairs, since I am counting the pairs of edges that appear in the same face. Now, if I fix a line and ask the question how many pairs are there which involve this line, that is nothing but the complexity of the zone of that line, because those were the edges where it is being counted as a pair. So, what it means, and I do this for every line. Now, if you fix a pair of lines, let us call this L prime. So, if you have pair, let us say L L prime. Now, when I count the notice that the way I wrote the sum, this pair is being counted twice. Once when I pull this line L out and I counted L with this pair H prime, and the second time when I pull this L prime out and I counted L prime with L again. So, I counted each pair twice, that is why I have 2 NF choose 2. Is that okay? Or I okay. So, last time I had asked the following question, that I give you a set of points and you want to find the minimum area triangle spanned by this by triple of these points. So, remember that the following problem I had asked. Set of points in R square, compute okay. So, you want to compute a triple, so whose area, so that if you look at the triangle, the area is as small as possible. So, for example, this might be the case here. Okay. Now, as we talked that n cube is a trivial algorithm, the question is how we do n square time. What we will do is we will use the duality. Okay. Before that, we make the following observations of following. Fix a pair of points P Q. So, let us fix a pair of points and let us look at ask the following question, which triangles I should look at that involve the pair P Q. Okay. So, there are n minus 2 such triangles, right, because you fix 2 of them, the n minus 2 points are left, with each of them you get a triangle. Out of this n minus 2, which ones we should look at? Okay. Now, since you are looking at the minimum area triangle, then the point that you should look at the points and you can sort them how far they are from this line, all right. And among them, what you have to do is you can think about choosing only one which has a minimum height, am I right. So, if you have all the other points, then you sort them by the line, and for each of them you only look at the closest one. So, in particular, if this in particular what this implies is that if this is a, let us look at do the both sides. I will be little sloppy and I look at the both of the stuff. So, if you look at this side, if I am going to look at if I am going to consider PQR triangle, then since this is the closest one in this perpendicular distance, then the strip that is I have drawn, that I drew the line parallel to PQ passing through R, this strip does not contain any point in it, am I right. Okay. The other thing you observe that since the slope of PQ is fixed, it is also fine, instead of talking about the perpendicular distance, we can also sort the points by the vertical distances with respect to this line, because sorted order will not change. Of course, the distance is changing, but the sorted order will remain the same whether you do by vertical distance or you take the perpendicular distance, because everything you are multiplying by the same sign of theta, where theta is the slope, this one. So, why am I saying all this? Any questions? Go ahead.
Sir, you sort them according to their vertical distances from what point?
From the line, PQ. So, you have this line P passing through PQ, take any point, look at this vertical distance and sort by this. Okay. Now comes the duality and why the duality will play a role. Remember that there are many forms of duality, and the one which I will use the following, that a point A B is mapped to a line B, and the line mapped to the point alpha beta. Okay. So, the nice thing about this duality is that the vertical distances are preserved. What I mean is that the vertical distance here is the same, well, certainly not in the figure, but this vertical distance here, they are the same. And it is not sort of is sort of different, because if you look at the vertical distance in the primal plane, it is basically b minus alpha a minus b. The vertical distance between P and L is b minus a alpha minus beta, and if you look at it here, again it becomes beta plus a alpha minus b, which is the same as saying b minus a alpha minus beta. Okay. So, the duality preserves the vertical distance, point maps to a line, line maps to a point, the vertical distance between point and primal, in the primal plane vertical distance between point and line is the same as the vertical distance between line and the point. Okay. All right. Now, what we are going to do is we take the set of points that were given to you, map them to lines, use this duality. Now, what does a line passing through a pair of points correspond to in the dual? Intersection of 2 points, am I right? Because if so, you have a the 2 points P and Q, each of them maps to a line in the dual, and the line in the primal passing through P and Q corresponds to its intersection point of the 2 lines. So, let us say that this was let us say this was P star, this was Q star. Then this intersection point of this one is okay. And now notice that what we are interested in, we are interested in finding a point, the third point, which has a minimum vertical distance from this line, am I right? And the duality preserves the vertical line, vertical distance. So, what that means is that from this intersection point, you want to find the line which has a minimum vertical distance. So, if you draw the vertical distance ray from this side or this side, this is the point you now in this case there is nothing up it, but suppose if you had chosen this one, then what you are interested in, these were these 2 lines you wanted to look at, which is these 2 points, that this point and this point that I drew here. Okay. Now, if I have the arrangement, then what do you do? So, which zone? Well, you do not have to do even that, it is simpler than this. So, what you want to do is for each vertex, you want to find the line that lies immediately below it and the line that lies immediately above it, right. That is all you need to find. So, if I give you the entire arrangement, you have computed the entire arrangement. You can compute the arrangement in n square time, right, because compute, first step is compute. So, this is S star, arrangement of S star, okay, compute the arrangement. Now, one thing you notice is that this vertex, the face basically on which you have to consider is the edge that you are looking at lies in the same face as this vertex lies, right. So, what you have to do is you have to traverse each face. So, you look at the one of the faces, you do the following for each face. Suppose you have one face, it has left and right vertex, leftmost vertex, rightmost vertex, you have top chain and you have a bottom chain. So, what you think about is you think about marching both on the top and the bottom simultaneously. Think about like merge sort, think about this is one list, this is the second list. You start going this one, and when you visit and you are marching in lock step, right. So, when the way you do in the merge sort. So, think about merging these 2 lists together, these 2 lists of vertices. When you reach this vertex, figure out which edge you are currently scanning, match this one with this one. Next time you will reach this vertex, then you see which edge you are scanning, this is this one. Then again you will come reach this vertex and then see which edge you are scanning here, and so on. So, just taking each face and scanning thinking of merging the top and the bottom boundary of this each is, and for each vertex you can find what is the edge that lies below it, and the same thing you will do it for each face, and this way you will have all this stuff. Traversing this stuff takes time proportional to the number of vertices here enough, and we know the total complex arrangement is n square. So, total time will take you is n square. So, this way you can find and you have all the triples you need. So, you can find the minimum area triangle in n square time. And the $1 million question is, can you do better? People believe that you cannot do better, but there is no lower bound. Actually, there is even a simpler, let me ask you a simpler question. A special case of this is, I give you a set of points, are 3 of them collinear, any of 3 of them lie on a line. This is a simpler problem. How will you, if I compute, how will you figure that out?
So you take the dual and see if three lines intersect.
Yeah, that's right. So if there is a vertex which has degree more than 4, it has degree 6 or more. If that's the case, then 3 points. That's right. So this is even simpler than this problem, somewhat simpler, am I right? Because that's a special case. And again, there is n square you can do easily, compute the arrangement and then check it, as you said. Can you do better than n square? There are some lower bounds in some strange models, but these models are very strong. What basically they say is that if you take an arrangement, there are kind of n square independent triangles, and that's what basically people have. But in the traditional models that use, or lower bound models that you see, like you have seen the decision tree model and some other cell pro model, or it's not known, and that's a sort of is a it's an open question. And this is in some sense related to what is called x plus y sorting. Have you heard of the problem x plus y sorting? Suppose you have two sorted lists. That is each of them length n, the two sorted lists, just real numbers, or if you like, you think of them as integers, it does not really matter. X plus y, set x plus y is as I wrote it last time. So, the set x plus y has n square items. You can easily sort them in n square log n time, all right. That is a triviality. Can you sort them in n square time? Because you have a lot of information now, because you know that x is sorted, y is sorted. Can you use this information to do the sort better than sort in n square time? There is no lower bound that you need n square log n comparisons, because these are not independent comparisons in doing it. So, that is a big open problem. And again, there are some lower bound which sort of proves, which suggests that you cannot do better than you cannot do better, but it is not known.
Even n square is not known.
No, n square is not known. That is well, you cannot do better than n square because there are n square items. So, can you do it in n square? That is not known.
So, for finding the maximal points in a plane, if we consider the values of x plus y for each of the points, then can we do better than n log n?
Sorry, say it again.
So, for finding the maximal points on a 2D plane, we argue that the lower bound for that is n log n, because you need to do comparisons, you need to do sorting on a particular coordinate. If you take the input as x, so if you take the input as xi plus yi equal to c, and this is satisfied for all points, then
So,
you essentially have to sort along x axis or something like that.
So now x is a set of points in the plane, or it's just a real number. So, when you say xi plus x plus y, so what are the so you have a set, you're saying that you, let's say, given a set x.
If I process my points, so
No, sorry, I'm not sure what the points are. Yeah, I'm still not. So, suppose you're given x as a real numbers, y as a real numbers, and you look at x plus y, you define as not xi plus yj. I suppose you're defining as xi yj.
xi
Yj you mean, because if I just do xi yi, then they are also taking the diagonal. Then
no, what I'm saying is I'm starting with the maximal 2D maximal problem.
yeah,
Right, so I want to figure out what the maximal points are on a 2D plane.
okay.
Right, and so I'm saying that can I do better than n log n
If
if I add up the coordinates of the points, and let's say I know that some set of ni points, they all like xi and yi add up to c for some set of ni, some set of points, and then
so if x, oh I see, you're saying that if all,
I'm saying I can draw these diagonal lines, and I know that some points lie on these diagonal lines, then I can do better than log n log n.
so if, okay, so yes, in some cases you can do, because if suppose if you know that the problem becomes simpler, because because what happens is that all the points that lie on a single line, if the line has a negative slope, then all those points will appear on the maxima. Am I right?
So I'm considering the line with the negative slopes only, right?
So yeah, so if you,
That instead of line sweeping like this, a line sweep like this.
so yeah, so if so you are raising a sort of an interesting question, because there are refined bounds. So people have asked a similar question for sorting, that suppose if you have only n distinct items, if so k distinct items, what's the lower bound on the sorting? And you are asking a similar kind of questions, that suppose if the points are degenerate, then can you do sorting better? And the answer is yes, and n log n does not hold in lower bound, the better lower bounds in that case, and that's what is happening in this case. So for example, like there are also results, for example, like if you give something bounds on the bits, that all the bounds have some bounded bits, or if you have some bound on entropy of this coordinates, then the better bounds are known. So the better bounds are known on sorting as well. So that's those things. So answer is yes, you can do some better. Any other questions? Okay, so what I want to do in the 5 minutes, let me do the following. So far I talked about the arrangement of lines, but you can talk about the arrangements of other geometric objects. So for example, instead of full lines, let us just look at line segments. And now you notice that if I just draw a set of line segments, and I can again talk about the arrangement, because who's the same way that vertices are intersection points, and also you need to talk about the endpoints also put as vertices. Now, but one thing you notice now is the faces are quite a mess. Let us see if I put even. So, if you look at one face, the face is a single connected component. If you mathematically it is defined the following: take the set of segments, think of them as a set of points, each segment, take the union of the segments of these points, remove them from the plane. Then what you did, you think about the plane and you erase something there. Just maybe think of making a cut along each of the segment. Plane is being cut into many pieces, and each connected component of this what is left is called a face. So, for example, now here is a very complex face. What you notice is that unlike lines, where each face was a convex polygon, is highly non-convex. Not only it is not convex, its boundary is also not connected. In this case, the boundary consists of two components. Okay. And then you ask the question, what is the complexity of a face? How many vertices can appear on a single face? It is no longer obvious that the number of vertices on a single face is only linear or near linear. It could it be as large as quadratic, all the vertices appear, and that baffled people for a long time. And it turns out that it is near linear, but it is not linear. So, the complexity of a face, so let us say S is a set of where alpha n is the inverse Ackermann function. So, I assume all of you know Ackermann function. Right, and the interesting part is that this is tight. This is, I wrote as theta, not as big O. So, there are set of segments for which a single face can have a complexity omega of n alpha n, and that is very strange, because alpha is not a natural function that you can you will think of. but nevertheless it is near linear, because we know that alpha is very small, has very small values even for very large values of n. Now, the face is very such a complex, because in the case of lines, the face was a nice convex polygon, it was easy to represent, and now it is very hard to represent, because how we represent such a face. And a common way of doing it is what is you have seen, I believe, trapezoidal decomposition. What you do is you take every vertex on the face and you draw a line until it hits another line segment. So I have drawn way too complicated, so it is hard for me to finish it, but what you do is that for every endpoint and from every vertex you draw a line segment, vertical line segment up and down until it hits something. And now what happens is that each face becomes a trapezoid or a triangle, and so it is much nicer, and then you work with this trapezoidal. So, this is called vertical decomposition or trapezoidal decomposition. And I will skip the thing again. We can construct the arrangement and this vertical decomposition by doing the line sweep, which will take n log n plus k log n time case number of vertices. There is a randomized algorithm that takes time n log n plus k, where k is the number of vertices, expected time. Okay, so let me stop here.